if people can start migrating towards seats. Jeff, you were in a seat, you got out of the seats, wrong direction.
Hello, hello. Yeah. I'll actually step aside.
All right, it looks like we've hit the 2 sigma points in people straggling in. Please take your seats as quickly and quietly as possible. So it's my pleasure to begin the first afternoon session of the ngEHT meeting. And so we're going to begin with the next generation of black hole imaging. And it's my distinct pleasure to introduce Remo Tilanus, Chief Operating Officer of the EHT, to tell us about EHT capabilities, current and planned.
Hello, yeah. I should have gone to for that, Chief Operating Manager. You know, that kind of has something, I like that. Yeah, let me first ask, who wasn't here on Sunday? Raise your hands. This talk is for you. Yeah, the rest of you has seen quite a bit of it already, but I put a slightly different slant on it. All right, hopefully it will now work. So I didn't know what kind of audience to actually expect here, but you know how many ngEHT people are and their familiarity with the EHT. You know, a lot of people are streaming into the ngEHT project, and so Max, I will start slowly and then introduce the EHT. So this was the EHT in 2022 with the observations, with 11 observatories and 9 locations. You know, Chile and Hawaii have 2 stations that are co-located. So that is a very large array already, and it is a marked increase from the array that we actually fielded to get the 2017 images. So since then we added 3 stations, GLT, and that gives us really nice north-south baselines. We added NOEMA. This is a very sensitive anchor station and gives us medium short baselines. So, you know, to translate that, we hope that we'll be much more sensitive to the, for instance, the jet that comes out of M87, the large scale structure. And then that's also Cape Peak, the short baselines, which will really help with that feature. This array has now supported 4 observations since critically ALMA joined the array in 2017 for observations. And we always are dealing with a lot of parallel data streams. So for 2023, we are currently actually handling the proposals. For 2021, the correlation, etc., etc. So the natural operation cycle on the operations side is already like 3 years. In order to get capability onto the telescope, you typically have like developments that last 2-3 years before that, and after you actually get the observations out from the correlation centers, you get the science utilization, and that can take several years before they actually have papers. So what do we have? Okay, so 2017 is now in the open market. This is the Granada Bazaar. Now all the data since 12th of May, all the data from the campaign are actually online, available for anyone to exploit. 2018, we're getting ready, I believe, to reveal an image of M87 from that, to see if we have any consistency. 2019, we lost out due to operational issues. 2020 then compounded that by giving us COVID. And so we came back in 2021 with the 3 new stations. In the meantime, we had upgraded, doubled the capacity from 32 gigabits per second to 64, which means from 2 times 4 gigahertz bandwidth to 4 times 4 gigahertz bandwidth. And so the 2021 and 2022 observations were with a similar array. The 2021 observations are, as we speak, are being correlated. The correlators are running. And the 2022 observations, all the modules are arriving at the stations, at the correlation centers right now. So the data is arriving. For 2023, we intend to actually give new capability. 345 gigahertz, it has been approved for observations, and proposals are in there. You know, we received 14 proposals, and 4 proposals are asking for 345. So I'm hoping that that will add something new. Besides these larger upgrades, there have been a lot of other upgrades that are not so visible and that are under the hood. And I don't want to go through them all, but passive phasing and ALMA was a critical one. It allows us to actually go to fainter sources. Backend control actually enabled remote control, remote operations during COVID, in fact, if you want to cut to the chase. And then we have, like, we standardized the metadata acquisition. We had upgrades, actually significant upgrades at the correlators. You know, they were enlarged, and DivX software has been upgraded to deal with complex stations like phase NOEMA. And then we actually had other, And then, for instance, we also have now e-transfer of fringes for verification. So the first time that NOEMA joined, during the campaign, we could actually confirm that we had fringes, which is kind of a capability that we did not have before, which is really nice. And in the meantime, our data modules have increased from 48 to 128. Wait a second, I don't have to walk back. Let me see. Yep. So I just want to say that technically and operationally, the Event Horizon Telescope has never been static. It is always evolving, and a lot of things are still going on. And so one of the things that is going on is that the Mark 6 recorders are being upgraded to double capacity. We're going strongly into the direction of agile observing. This is to simply make it possible to switch on the array much more easily or transition into VLBI much more easily than we've been able to do before. And this implies things like that the calibration of the source, the calibration, that the calibration source can be switched into the stream automatically, remotely. We are doing spectral line. Spectral line will be released almost, it's still not certain, but we expect that spectral line will be released for VLBI from the 2024 campaign. So that will give us access to the Mesa community, access to the millimeter VLBI regime. New dual frequency receivers are actually being developed. For the LMT, the ngEHT project, Gopal will actually talk about that. And NOEMA will actually expand the number of receivers that they have at 345 gigahertz, also in that time scale of 2024-25. All right, we'll see the addition of OVO from the ngEHT project, and the KVN we've heard about before earlier this week. They are working to actually they're building a new antenna in Korea that will actually hopefully become operational around 2024. And they're using multi-frequency phase transfer to enable that site. And this is a critical technology that will also help us in the future if it actually works well. VLBI backend corrections, we're working on the data actually to make all the data handling more sophisticated, etc., etc. So there's a lot going on already. More details you can ask about any of these details later. What I want to actually really talk about is a little bit the longer future, is where can we go with the existing equipment, and then the phasing in with the ngEHT project. And that is, it is actually fairly simple how this actually works. So first of all, the VLBI, the current backends that we have at the single disk stations, which schematically just are the receiver. We have block down converters that split up the frequency bands for the digitization. So the digitizers only take a small fraction of the bandwidth. So you have to have multiple of those. And then actually after the digitization, the digital signal gets put on the Mark 6s. So those are the components. Those are the components we have to upgrade in the back end. Now the first upgrade is easy, and it was actually on the previous slide. Because we have to upgrade the Mark 6s due to obsolescence of components, we actually think that we can get this transition for free. Mark 6s in the lab have already been shown to operate at this frequency with this data rate. We just now have to make it reliable enough to also use this data rate in the field. So this is actually ongoing and irrespective of any plans towards dual frequency. And dual frequency here means simultaneous. Right? This doesn't mean that we do one night we do 230 and the next night we do 345, which is a capability we will use, of course, in 2023. This means that you actually at the same time get 230 and 345 or any other frequency. The block down converters actually that split up the bands, you know, it's kind of, we should have been smarter. They currently are configured to give you a filter set 1 or filter set 2. Which corresponds to 230 or 345. And we just need to reconfigure them to give us filter set 1 and filter set 2. This is a minor reconfiguration. There actually are already kind of block down converters in the field that have this kind of configuration. So it's easy. And you can see here a block down converter with 8 blades that are each 2 gigahertz apart. So each block down converter already supports 64 gigabits per second, and we have 2 at most stations. So we already have 128 gigabits per second, the 2 times 64 that we need. In order, slightly less known is what to do with the digitizers. There is a backend available that actually will do 128 gigabits per second. It's the DBBC3, and it is actually used in 2 of our stations already. But on this time scale that we're talking about, there may be new 128, plus digitizers already, maybe from the ngEHT project. So how exactly we're going to solve this, the details, we'll have to look at that. But it is fairly straightforward. If it needs to be in order for DBBC3s, then in about a year that will be available. More difficult is the projected dual frequency capability, because in this plot, we actually didn't talk about the receiver. Not all telescopes have dual frequency receivers. And so where do we stand with that? ALMA does not have dual frequency, but it supports rapid switching. In fact, Violette can actually correct me. She's like, what? Can correct me that if you actually have integer ratios for the LOs, it can switch in something like 10 seconds. So that is faster than we actually need. But that just gives you the capability that, from one scan to the next, you could in principle switch from 230 to 345. Now, the LMT, I said, and the SMT will actually are working towards the new true dual frequency receivers that will actually have both frequency online all the time. And Gopal will talk about it, as I mentioned. The KVN, and there's also talks about, phase transfer later this week, is working toward the triple band. SMA can do dual frequency, but it's a single polarization only. Apex is actually now considering how to actually make multi-frequency available. Yep. And we have like 30-meter telescope and NOEMA. NOEMA currently can already do 86 and 230, and NOEMA is building receivers for that. And these other telescopes will need upgrades to do it. So it's not going to be a wholesale conversion. It will be a gradual conversion that will happen. And, the ngEHT developments, of course, how quickly they will actually be able to deploy certain receivers will also come online. And then we'll actually also actively investigate phase transfer. There are a lot of open questions. I'm not going to spend too much time on these. You can actually read these. At some point, we may end up with an array that is actually 80 gigahertz, 230, and 345. You know, some base rates at 86, and it is, you know, we just have to look in how useful that is. Now, what is actually in terms of UV tracks? I said baselines on Sunday, but you know, Vincent correctly pointed out what I mean is UV tracks. We did the observations in 2017. That were the only observations, of course, that we've published that you've seen, with 10 to 15 baselines, 10 for M87. If we add these stations, and I don't know what happened here. I mean, I call it this. OVRO is actually a target of the ngEHT project, and Haystack is also another one that is delivered by the ngEHT project. We can go up to about 72 UV, you know, baselines, UV tracks. That is an increase already for M87 by a factor of 7. If you then actually add multi-frequency tracks, you can go up to something like 120. That is actually an enormous increase, and you can actually, you move from a sparse array to a substantially denser array. And yeah, if you then also actually go to add the small dishes that the ngEHT is planning, you come somewhere up here, you know, to an array of 20 dishes. So this, I think, is a very natural evolution of the millimeter VLBI array, you know, in general terms. You know, I don't want to put labels on things. So in general terms, collectively, this is where the community is moving to, and this is not stretching it. There's actually a third possibility to generate more stations, and that is if you do phase transfer and the telescope service supports it, you can actually get to that. So there are like 3 different ways in which you can get substantial increases of the telescopes. So it's kind of logical to expect that that will get there on that time scale. And then you can see here such expansion will come with things. We have to have a very good organization of the operations and, you know, scale those, and further critical developments to the data structure. So let me talk a bit about near-term operational roadmap. And this was the technical side. So where do we go on operations? And I won't again spend too much time on this. I mean, I'm already told that probably have 2 minutes. All right. And so that is this slide. The content comes from Violette, but I actually mangled it up. So if there are any mistakes, those are mine. But you know, the spectral line capability that comes online in 2024 will give access to masers. You know, both galactic maser and extragalactic masers, and you can see, you know, galactic masers, you get astrometry, proper motion around evolved stars, for instance. Extragalactic, you actually start mapping, you know, the AGN accretion disks at very high resolution. But you know, submillimeter masers are largely still unexplored. So this is a new area to actually look into. Extragalactic absorption lines are another thing, and they actually can be very sensitive and reveal the physical environment, you know, around supermassive black holes, and even in cases where there is very diffuse gas, you know, in the jet ISM. So that is one aspect that we want to look at, the spectral line. Secondly, dedicated time-sampled imaging of supermassive black holes. So we want to actually start looking, what does it take to get a movie, right? Which is one of the main ideas behind also the ngEHT. But you know, you have to start, you have to learn. So we want to start that, and we have actually this capability to do that. You know, we may actually be able to fill 2 sets. You know, so we may actually have quite a lot of time available in terms of storage capacity. Open questions. You know, what will we do? We'll do M87 and or Sagittarius A star. These questions are being now being started to be discussed by the EHTC, by the EHT collaboration, and a lot of you are part of that. Then secondly, you know, my suggestion, just to give you a sort of a framework to think about it, For M87, this may be a series of 230, 345 observations that are closely spaced in time. But then, you know, these observations span in total 40 to 60 days, or maybe even 100 days, if we actually can get access to the telescopes for that amount of time. Not every day, of course. We'll do one observation a week roughly, or something of that order. Sagittarius A star would be different. There we would actually want to have as dense as possible, you know, a series of 230 gigahertz observations only spread over a few days. Now, how is this going to, so again, all these things are under discussion, and, you know, your participation is in these discussions is highly appreciated. But the first proposal for 2024, the actual proposal for 2024 will need to be formulated by April. So we need to make decisions. And I told you for 2023, we're going after, for the first time, 345 gigahertz VLBI. And 2024, now the question is, where do we go? We can go for a dedicated spectral line run. The reason why I wanted to be a dedicated spectral line run is, first of all, it gives us a breather on the ngEHT side. We've collected a lot of data, but also we only need a few modules, right? We're not going to have all the full bandwidth. We're only using part of the bandwidth, and we're saving actually modules for the time sampled imaging. However, if we are ready, we can actually go for time sampled imaging in 2024, or we do it the other way around, right? And so OVO should be able to join us in 2024 or 2025. Perhaps, maybe that's a little bit optimistic to have Haystack in there, but I wrote this particular slide quite a while ago, but we'll see. So this is actually, to give you in a nutshell, sort of what I've proposed for the coming years. Nothing is set in stone. This needs to be discussed. It needs to be discussed with the observatories. It needs to be discussed with ALMA. ALMA is in fact thinking about how they might be able to facilitate a run that actually spans 2 or 3 months. But we're still working on that. I think that consumes all my time, so I'll leave it at that. I hope this is giving you a little bit of an impression where the ngEHT hopes to be moving, the current array hopes to be moving over the next few years. Thank you.
Thank you. I think we have time for maybe 1 or 2 questions, but Shep, can you start making your way towards the stage? So are there, yes, please.
I'll say.
Thank you very much. Nice talk. When do you think it will be possible to have TOO observation with the ngEHT?
Sorry, the sound, it's very hard quite often from on the stage to hear what is being said in the phone. So what was being said? Ask?
Yeah.
Do you know? No? I can.
I asked about when it will be possible to do TOO observation.
Oh, TOO observations. I don't know what you mean by TOO observation. If you happen to actually if you have a target of opportunity close to the time that we observe,
Yes.
there is a slim chance we can fit it in, but officially we do not have TOO capacity. All projects need to actually be approved by ALMA, etc. And the time allocation gives that. So officially we don't have it.
But is it possible, for example, negotiate with ALMA to have some kind of time which is possible to spend during the year, so that if you
when will you know when you have a TOO? You know, I mean, how much time do you need? How much lead time do you need?
This sounds like a wonderful.
Yeah, I got actually.
This would be.
So the simple part is it's not there right now.
Yeah, what I guess it's Granada is thinking about, you know, neutrinos and so on. So do you need to move to start observing like half an hour after the trigger? So these are really very quick things.
It's impossible because we need schedules. Without ALMA, it is remotely possible that we could do something like that with only the EHT array, not ALMA.
Quickly about ALMA also. Frequency phase transfer is really extremely powerful, but 10 seconds between 2.3 and 3.45 could be, a killer for transferring the phase from 2.3 to 3.45. But what about subarray? Is possible?
Oh yeah, so yeah, of course. I mean, we don't plan to switch ALMA in 10 seconds between 2.30 and 3.45. We're not going to do that. I'm just saying it can do it. But subarraying, unfortunately, it was not included in the APP project, right? So that would be a next development that would fall under the APP flag.
All right. So Svetlana, let me just say that operations mode's really an interesting question. We might hear more about that later in this session.
Great.
Let's everybody thank Remo again.
Yeah.
All right. And next we have Shep Doeleman, founding EHT director and the PI of the ngEHT project. And he'll be telling us about what the ngEHT is and the vision. Take it away.
Okay, can everybody hear me? Excellent. So thank you very much to Remo for telling us where the EHT is going to go. And of course, as I mentioned earlier today, the ngEHT builds on the EHT and plans to go as far as we can take millimeter VLBI observations of black holes from the surface of our planet. We are not going to be discussing space here today, but that's for a different time. But the idea here is that we've observed these two supermassive black holes. We've now entered the regime of precision measurements of supermassive black holes, and we'd like to expand the array on the surface of the Earth to take this as far as we can go. Okay, so just so I know there are some people joining us who have not been in this universe before. So we use Earth rotation aperture synthesis to fill in these virtual global apertures to make our measurements. Each point here is one Fourier component of the brightness on the sky. And when we measure many of them, you can make an image. And in 2017, as Remo pointed out, we got the entire band together, the first EHT observations with fully 8 stations altogether. And the images of M87 that you saw before were made with 5 geographic locations. So we really made the most of a very sparse array. And you can see all the Fourier coverage here. And we used $1 billion of existing infrastructure. So we brought bespoke electronic instrumentation to observatories all across the planet. And together they were able to do what no one of them could do by themselves. Now, one of the secret ingredients, although perhaps not so secret for the EHT, was the fact that we followed Moore's law in our capacity. So the signal to noise ratio of our measurements is directly related to the recording rate. And Remo talked about many, many gigabits per second. So we started off in the early 2000s with reel-to-reel tape recorders, and we were able to record, let's say, 224 megabits per second. And now we're recording 64 gigabits per second, a startling increase made possible by 13-year-old gamers everywhere who have propelled commodity electronics to the point where we can order many of the components of these instrumental setups at all of our sites directly from Amazon, let's say. And the secret ingredient here is the software that binds it all together. Now, of course, we want to do better for scientific reasons. So, this is a simulation showing the supermassive black hole here and the jet leaving supermassive black hole energized by M87. And in 2017, we were able to measure this inner part here, but not the faint jet. So we can't study the jet progression past the supermassive black hole. And to do that, we'd need a dynamic range of about 1,000 to 1. Similarly, as you've seen earlier today, black holes are very dynamic objects. And for Sagittarius A star, GM over C cubed, the light crossing time of the horizon is 20 seconds. And the period of the innermost stable circular orbit is about 30 minutes, a little bit less, a little bit more, depending on how you're moving around the black hole. So we need, if we're going to make movies, to take frames of this object on a sub-ISCO period. So maybe every 30 minutes or every few minutes, we have to make a new image of Sagittarius A star. So how are we going to do this? Well, the idea behind the ngEHT is that we can survey many sites around the globe. And in a complete change from our approach to the EHT, instead of using only infrastructure that exists, we want to put new dishes around. And we reasoned that with about 10 new small aperture dishes, a bandwidth expansion of about a factor of 4, and dual band observing that merges 1.3 and 0.87, we could significantly expand the capabilities of the array. And what you see here is the 1 sigma sensitivity on a baseline between a small diameter dish and one of these very large anchor sites. And if this is about our projected sensitivity, in 1 second, you get about 10, 20, 30 millijanskis of noise. And in 100 seconds, you wind up getting about 3 millijanskis of noise. So we can get down to about this level here, taking a small 6-meter dish and pairing it with one of the large anchor sites. Now that's important for the following reason. So Jeff Bauer showed these plots before. This is all the data that we have for, I'm sorry, these are mixed up. That should be, hold on. There we go. So this one is Sag A star, of course, and this is M87. But this is now a 5 sigma limit. So everything above here can be accessed by one of those 6-meter dishes. Everything above this line at the 5 sigma level can be accessed by a 6-meter dish. So the key point is that small dishes suitably located on the surface of the planet can greatly expand our Fourier coverage and be sensitive to all of the data that we need them to be sensitive to. So we submitted a white paper to the Astro 2020 Decadal Review in the United States, which is that navel gazing exercise that happens once every 10 years in the US, and there are similar kinds of reviews elsewhere. And the idea here is that on this angular resolution versus frequency plot, the ngEHT occupies a very interesting space where over a range of frequencies, we can resolve the black hole shadow. We got a very nice positive mention in the radio millimeter and submillimeter panel report. And of course, this is the latest incarnation of us getting the global community together to start thinking about the science that can be done. Now, when you think about where to put these stations, the first thing you look at is what are the high elevation sites? You want to be above the water. So there's very few places where you can reliably get above 2,000, 3,000 meters. That's one of the first cuts you make. The second cut you ask is, where can I take advantage of the existing EHT sites? And it turns out that for M87 in the blue and for Sag A star in the red, you can see where you'd like to put your dishes to have the maximum overlap with the existing EHT, right? So preferentially here in the Western Hemisphere, but also, of course, over here in Africa as well, and in some cases in East Asia. And we asked, how do you determine where to put these sites? And there's a number of different figures of merit here. So we looked at UV filling factor, we looked at the largest circular gap when you add a source, what is the biggest gap in the UV coverage, and we also looked at imaging techniques, seeing when we added a site, how well we were able to recover known images. And it turns out that you can make a pretty reliable phase 1 determination of where to put the sites that would have the maximum impact. So phase 1 of the ngEHT, as we've currently defined it, would give us significant near-term increase in functionality from 2022 to 2026. All the blue sites here, Ovro, Baja, Haystack, Canary Islands, and Las Campanas, for example, wind up taking you from this UV coverage here in the bottom in 2022 to this UV coverage. Fairly large fraction increase. At the very bottom, you'll see here, we go from about 28 baselines to around 123 baselines possible, or an increase of about a factor of 4. This is a pretty large increase. It allows us to do some very, very interesting science. We're refurbishing dishes. We're studying, designing, and prototyping new dishes, and we're upgrading existing facilities, as Remo described, to much higher data rates. Now, the second phase is longer term. And here we're taking the ngEHT dish that we're going to design in phase 1 and replicating it in even more sites, 5 more sites around the globe. And now compared to 2022, we're looking at nearly filled UV coverage. So we're going from that sparse coverage that we had before, where we're barely able to make out this ring, to an area and a regime where we can get much higher dynamic range. and look at the jet as it flows from the black hole, for example, or make time-resolved movies. Now we're looking at nearly an order of magnitude increase in UV coverage by the end of the decade. I'm not going to go into too much detail here, but we're looking at refurbishing these BIMA dishes at very attractive costs, and then new ngEHT dishes. We're in advanced discussions with some vendors, and we're looking at cost estimates and design for those. I'll be talking about that a little bit tomorrow. So what can you do with these kinds of arrays? Well, this is one of the GRMHD simulations that shows the black hole here and the jet expanding off to the right. And this is what we can do with a complete phase 2 array. But it gets better than that. Of course, if you observe, as Remo said, synoptically over many, many days, over about 2 or 3 months, then you can wind up seeing an actual movie with energy being extracted from the black hole and flowing down the jet. For a Sagittarius A star, because it changes so rapidly, you need to capture multiple frames in a single night. And this shows here the simulation. That simulation just blurred. And in the inset here, you see the UV coverage as it changes moment to moment. Some of the points here in red are 230 gigahertz, and the blue is 345. And you can see that you still get enough coverage to make frame by frame movies of Sagittarius A star. And this is the reconstruction using a dynamical imaging algorithm. So for both M87 and Sagittarius A star will definitely be in the regime. We can start making time resolved, high definition, real black hole cinema. Now, can we do better on tests of GR? Well, we can. I think Michael Johnson's going to talk more about this. This is really his brainchild along with Alex Lupsaska. But this ring here is separated now into multiple rings based on how many times photons orbit the black hole. And the n=1 ring is very, very thin. You'll see it here. The photons spend more time deep in the Kerr metric, and it's a very, they lead to much better tests of the Kerr spacetime. And the n=1 response here, think back to Jim Moran's talk with these nulls here, can be extracted because the n=0 has been resolved out. And we'll be able to do this. It shows here that with the EHT coverage, it's very difficult to do. Even with the ngEHT coverage, just with 345, it's quite difficult. But when you add 230 and 345, we can start extracting the n=1 ring and make very sensitive tests of GR. So where are we? We have a couple of large grants from the NSF and from the Gordon Betty Moore Foundation. We're looking at enhancing the current EHT array, looking at dual band receivers, as Remo said, LMT and daytime operations and so forth. We're planning the ngEHT next generation of instrumentation and antennas. And the GBMF, the Gordon Betty Moore Foundation grant, specifically supports key developments that will benefit both the EHT and the ngEHT. And the output is a full design and a material that's suitable for the next round of funding proposals. And this supports and enables a large international effort. And I really mean that. The whole reason that we're here at this meeting is from this kernel of an idea, we want to generate an international community. It's going to look at the science and the instrumentation and the implementation. So Michael's going to talk more about this, but we have multiple working groups led by people from around the globe, looking at all the different science possibilities one can do with a millimeter VLBI array like this. And I want to call attention to the fact that we've had 3 meetings so far for the ngEHT. And specifically, I want to give a shout out to a few people here. Avery has been the co-chair for the first 2 and also on the SOC for the final meeting. So he's been in all 3 of these. And he's been a real leader in organizing a lot of the science here, in addition to Michael Johnson, who's the project scientist. And also Jose Gomez was one of the SOC members last time and is now chairing and is of course, our host. So thank you to both of them for their leadership on the science here. So I'm going to wind up here and just say that we've formed these working groups. We're here meeting today to refine some of these. In addition to these working groups, we have technical working groups looking at things like data management, receivers, and digital signal processing. The phase 1 sites, we think we've settled on those, but we're still doing some fine tuning on that. And we are aiming to have new dishes on the ground, hopefully within 2 years. So it's extremely ambitious, but also extremely exciting. So within a couple of years, we should be adding up to 5 new stations to the ground array with real increase in capacity. And this meeting is key. We're going to discuss the science traceability matrix. Michael's going to introduce that to us soon. We're going to look forward to the concept design review down here later this year. And we're connecting to new facilities. And this really echoes Priya's talk and Sarah's talk, where they made very clear the connection between next generation facilities, not just this one. And we're working, of course, as Remo said, with the EHT to align all of our joint efforts. And this is the basic timeline here. So look forward to a great meeting, and we would like to answer any questions you have.
Well, thank you, Shep, for staying
Oh, was I well within time?
well within time.
Well,
Can't drop
we're
the
VLBI
masks.
people. We're down to the nanosecond.
Yes. Okay, so we have plenty of time for questions.
That was pretty self-explanatory, wasn't it?
Jose, please.
So in phase 1, can you remind us, so the plan is to have,
So I just can't
for phase 1, can you remind us that the plan is to have 5 new dishes those will be overall, and those would be,
So,
Haystack?
one of the configurations is still open to some discussion, but it'd be Ovo definitely, potentially Haystack, and then 3 new sites where we place the refurbished Bima dishes. One place could be the Canary Islands, another would be Las Campanas in Chile, and the other one would be Baja, Mexico.
so most of them in the northern hemisphere. So I guess so the phase 1 will be mostly focused on M87.
Yeah, a lot of thought went into this, and it seems very clear that for the first phase, we'd like to focus on M87, where we could start making these measurements like every week to have a first attempt at a movie. And then we would broaden the array in phase 2 so we could focus on Sagittarius A star. That's the general trend.
Andre, please.
Sort of that's asked this question of the SRR, but maybe you could elucidate it as well here. How much in science applications, how much in ngEHT we have to rely on the availability of facilities like ALMA, and whether we should not think about the range of science, but external participation, one that you simply with this new set of issues.
Yeah, this is a very good point. Michael, I think, is going to talk a little bit more about that. But so, for example, the movie that I showed with M87 does not include ALMA. So you can get enough signal to noise ratio from other anchor sites. So you don't necessarily need the firepower of ALMA to do some of the key science. And it could be that ALMA will join for some of the time and then not for other parts of the time. And you can still make very, very credible movies, even for Sagittarius A star, without necessarily lighting up ALMA. So at the same time, there are a number of science cases, astronomical masers and AGN, where we can use just the ngEHT dishes or a small subset, or even 1 or 2 anchor sites. And that would be enough to do that. Michael's going to introduce at some point the science traceability matrix, and we've gone through every different scenario on which science requirements will require which arrays.
So Shep, maybe I can use my prerogative and ask, you described the extreme value of having many more sites. Of course, that's the hard direction or axis in which to improve. But what about improvements in the back end that ngEHT is planning? Are there similarly transformative improvements in that dimension?
Yeah, I think going to a factor of 4 increase, I think is pretty significant. I mean, it's no longer transformative, but it will allow us to record double the bandwidth, and it will allow us to record simultaneously the 2 frequencies. And having the simultaneous 2 frequencies is the key, in my view, to unlocking the achromaticity of the photon ring, and it allows you to tease out the chromaticity or the spectral evolution of the jet. And so that is going to be, I think, a big advance.
All right, wonderful. So let's thank, oh, okay. One more, go ahead.
I wanted to follow up on the question, I think similar way to what Andre asked, from the point of view of the say the community, the ALMA community, for example,
For the what?
from the point of view of the community at large, would it be possible to use this facility also from outside the ngEHT collaboration and say an ALMA observer, especially because it's going to be so much more sensitive, it actually opens up to much more science.
Yeah, it's a great question. So the question was, will everybody be able to use this array? I think absolutely. So if we're going to go to the National Science Foundation, to other global funding agencies and ask for money to build out this array, which will be circa 100 million, then we're going to have to also have a component of that where people can apply for time on it. I think that's essential. And there'll be some key science that is going to be focused on the horizon, some of the main science drivers that have led us through on the EHT to where we are now, but there will also be a healthy swath of science that people will be able to apply for.
All right, let's thank Shep again. Okay, I'm not supposed to be this entertaining. Next we have Michael Johnson, the ngEHT project scientist, and he's going to tell us more about the key science goals of the ngEHT.
Okay, is the mic okay? Can you hear me?
Yes.
Excellent. Okay, so it is such a joy to be here with you today. We really appreciate you making time to travel in such difficult period and join us here for the first in-person meeting, a chance to talk face-to-face about all the work we've been doing over the past year and a half. I want to especially thank Jose Gomez and his group here for being incredible hosts. This is just such a special way to kick off the project. So what I'd like to walk through is where we're at on the key science goals of the ngEHT, how we got here, and what's next, what we want to get done this week. And the first thing I want to start with is just these pictures of Sagittarius Star and M87. We've seen them many times, we've discussed them a lot, but something that you might not be completely aware of is just how big of a leap these were over the previous best images. So here they are for both sources. Don't be fooled, on that one on the left, that dark region in the middle is the brightest point on the image. And these are not from 20 years ago. This is not a historical talk. These are from a couple of years ago. It's incredible. I think it was even incredible to us in the EHT, just what a dramatic change it was to go to 230 gigahertz. And the inspiring thing here is that we think that there's the capability for the same dramatic change, dramatic leap in capabilities with the ngEHT. And here's just a couple of reasons why. So here on the right, you see the UV coverage or the visibility amplitude is a function of baseline length. And I just want to highlight that half the flux there in M87 is completely resolved out by the EHT. We know there's a jet, we know that there's flux there, and we know that we don't have baselines to see it. So we have something that we absolutely can study, but there's no way to get around adding new telescopes. This is not something that algorithms are going to magically solve. We need new sites and better UV coverage. Now, our other guide here is theory. So we have these amazing GRMHD simulations. The one shown here, you've seen so many, but the one here has 1 second in this movie corresponding to about an hour of observation for Sagittarius Star or 2 months for M87. Now, these models reproduce very well all of the observational features that we have, and they predict that we have the chance to see entirely new signatures of relativity near a black hole that have never been observed. So just a few examples, they predict that there's a deep black hole shadow, a signature of the event horizon that's trapping the light and matter within it. They predict that there's a sharp photon ring that results from strong gravitational lensing that Shep mentioned. They predict that there's this dynamic accretion that's driven by magnetic instabilities and shaped by frame dragging in the rotating spacetime. And they predict that there are relativistic jets. They're actually here on the simulation, but they're so faint that you can't see them. So these are being powered potentially by the spin energy of the black hole. So incredibly fundamental things that we can tackle if we can make a more capable array. Now, just a couple examples of the breakthrough science that we could do. On the left here, that's a simulation of M87. It's not frozen, it just looks like it, but just to put it in context of how little it evolves, even if we stare at it for a full night or even a week, it's really jaw-dropping. And so this is not a heavy lift, right? All we have to do is extend our observations. The EHT observes for a week. If we can observe for 6 months, we can make movies of M87. And so that's a targeted goal. In M87, we know there's a jet. It hasn't been seen in ngEHT images. In Sag-A-Star, we now have models that predict exactly how much flux should live in a jet, and we have the chance to go out and look for it and detect the jet in Sag-A-Star for the first time ever. So many opportunities that are tied to clear instrumental advances where we know exactly how to do them, and it's our goal as the science team to define very sharply defined instrument requirements to be able to tackle these fundamental questions. So Shep put this plot up. On the left, we have these upcoming radio facilities, and on the right are the emerging infrared facilities and even VLTI there that we heard about from Frank. And at the bottom, you see the ngEHT coverage that achieved this in 2017. It's just a sliver of this parameter space that was responsible for this breakthrough science. In the ngEHT, we're exploding that frequency coverage by a factor of 10. We're adding short baselines to go larger field of view. And so it's been our job as a community to think, like, what is the unexplored potential in this new space that we're going to design the instrument around? So this process really started more than a year ago at our first meeting, where that was an exercise of just bringing everyone together and brainstorming, hearing all the crazy ideas that we could come up with and trying to understand the scope of the problem. Next, we got together in November. So we had another virtual meeting, of course, because of COVID. But here we were trying to be a little bit more focused on the instrument that was needed to attack that science and to understand what things are really out of reach for the near future. You know, we're talking about things, Shep just mentioned deploying new sites in 2 years. So we wanted to know what's really possible on that timescale. So we structured this around 8 science working groups. The coordinators here have been incredible. They have had heroic efforts at corralling all sorts of input and turning it into sharp summaries of the science cases in many different domains. So structured around these working groups, we also had new tools. So this is a particular app that was developed by Avery Broderick that allowed easy simulation of ngEHT capabilities for input images. So this was our chance to take those science cases that we've been brainstorming for months and really start to see what was viable. Next, we all came together for science requirements review. So that happened in February of this year. And the science teams put a huge amount of work into coming up with summary write-ups of their main science goals and associated presentations. So the goal here was to take all of these different ideas and distill them down to just a few science goals that would define the architecture of the ngEHT. And we had a great review panel for this. I want to highlight especially Jim Moran, Jeff Bauer, and Maria Felicia de Laurentiis, all of whom actually are speaking today, and served on this panel. It was an incredibly helpful exercise for us. They gave us very sharp feedback, and I hope that we can continue to discuss that this week. So we took all of that and we tried to distill it down into the basic set of what are the key science drivers for the ngEHT. And for these particular ones that are shown, these are what we call threshold goals. Okay, so we're not going to build the instrument unless we can achieve these. And in order to do that, these goals had to be demonstrated to be community and expert-driven priorities. They have to be uniquely accessible to the ngEHT. It can't be something some other facility can do and we're just confirming. And they have to be viable. We have to convince ourselves that with simulations and study that these are actually credible objectives. So these threshold goals are in 4 categories, extending from fundamental physics, accretion, jet launching, and black holes in their cosmic context. So these are goals that take us all the way from the horizon out to the scale of galaxies that you heard about from Priya earlier today. They're really an expansive set of goals. And I'll mention the specific requirements associated with those in a moment. And in addition to those, we also identified a bunch of other exciting science opportunities. So we call these objective requirements for the array. These are things where we think that these are absolutely things that can be studied. We can adjust the instrument to make sure that it's able to tackle these, but they're not absolutely foundational. So it's a different category. We think that these should be a major part of the science case. Now, we've had a lot of discussion about things like the ALMA and the other EHT sites. They join for a few nights a year right now. It's not clear what their commitment could be in the future. And so it's really hard to structure the array and tie that to science requirements when it's so heterogeneous. So just to walk through, here is the current ngEHT. We've seen this many times. This is the ngEHT as it operated in 2022. Here, each circle is proportional to the dish size at that location. So you can see we have these big sensitive anchors at ALMA, LMT, NOEMA, and so forth. Here's the phase 1 array that Shep mentioned. It adds 5 new sites. Haystack's a 37-meter. You can see it's big and sensitive there. Ovo is a 10-meter dish, and the other are the smaller dishes that Shep mentioned. So this is something where we would envision a near-term deployment with a small subset of new dishes. And then here's the phase 2 array that's adding something like 5 new sites. Okay, so this is not absolutely locked in, but it's a starting point for us to benchmark our expectations for simulations. So in our simulations, we're interested in exploring, what can you really do? So we're not just looking at when you throw every telescope at a problem. We divided it into different configurations. In the full configuration, it's sort of like the current ngEHT operating mode. Take every telescope you can get. And we would envision that you can maybe only do this for a few nights a year or a week or 2 weeks like current ngEHT campaigns are structured. In the partial array, we've dropped all the phased arrays in the ngEHT, and we've tried to reduce it down to a more slender set of the sites that might be able to join for longer, say, monitoring campaigns. And we're also interested in thinking about if we have these new dedicated sites, what can they do with minimal support? If they just have a single ngEHT anchor like the LMT, is there a key science that they can achieve with that? So here's just one example of how we benchmark these capabilities. This is a reconstruction of M87. So on the left is a so-called gamma or square root color scale, and on the right is a log color scale. And this is showing what the image would be with the ngEHT 2017 coverage. This is a great point of reference because we know what ngEHT 2017 images actually look like. So this checks out. It's a faithful representation of our abilities. Now, what we can do is we can say, if we extended that to time coverage, what kind of movie could the ngEHT reconstruct? So in 2017 coverage, not much. With 2022, ngEHT is adding these new sites. We start to get some information about where the jets live. With phase 1, we see the dynamics in exquisite detail. And in phase 2, we really see those dynamics extend out to tens of Schwarzschild radii. So these are the types of simulations that we're using to make contact with the science and understand what subset of the array really is needed for each of these science goals. Now, these are all collected into a science traceability matrix, as Shep said. There's a lot of information here. I'm not going to go through it all, but Aaron's going to walk us through tomorrow a little bit of the process of how we created this. I just want to zoom in on a few key things. So the key science goals you'll recognize from the earlier slide, and we're dividing them up by source. Right? The requirements to make a movie of Sag-A-STAR are wildly different than the requirements to make a movie of M87. Sag-A-STAR requires a few hours, M87 requires a few months. So we necessarily have to break it up by source. Now, in addition to that, we're trying to decide exactly what the operational configuration would be required. So here we're actually saying there's a lot of key science goals we think we can do with just the phase 1 array. Some we think require phase 2, in particular the Sag-A-STAR science. And we're trying to just get the highest level set of requirements that would allow us to achieve these goals. And then finally, we have to look at the array requirements, things like the observing frequencies that are required, whether they require simultaneous multi-frequency imaging, the image dynamic range that's required, and so forth. And here, we're really focusing on the difference between imaging and modeling, as Jim talked about. These upper ones on photon ring detection, we're never going to read that off an ngEHT image. So we're trying to distinguish that in the STM to make sure that we're defining credible predictions. So here are some examples. Detecting a black hole's photon ring. First, we have to say, what do we really mean by that statement? So in the STM, we try to make it as precise as possible. Statistically significant detection of persistent thin ring feature corresponding to n=1 photon ring. This is photons who went around the back of the black hole before they came to us. And each of those is precisely defined. Then we set up these simulations. So these are ones where we actually simulate the array, fringe detection thresholds, calibration errors, and so forth. On the left, you can see the posterior for the thickness of the ring. And on the right is the UV coverage. This is for the ngEHT in 2017. You see the true image there and the reconstruction next to it. Now the dashed line, dashed vertical line is the true width of the n=1 subring. That's not what we're after. What we're trying to say is we're trying to be able to constrain it to be less than 4 microarcseconds. That's the STM requirement. So that's our threshold for success. So in ngEHT 2017 coverage, we cannot do that. If we go to ngEHT in 2022, we still can't do it. The posterior is wide, the thickness of the ring is unconstrained. In ngEHT phase 1, we start to see those longer baselines really allow us to get a sharper handle on the thickness here, but we're still not at a 3 sigma threshold. And here's ngEHT phase 1 with a full array, and that's what finally gets us below threshold. So this is not a guarantee we can do it, but this is a bracketing requirement for us to define the array. And it's a step for us to understand what is really required and what's really a credible claim. And these are the things that we really have to flesh out as a collaboration. And what's amazing is that if we go to phase 2, it actually doesn't sharpen the posterior anymore. We've saturated the ability to do this with the LBI without going to longer baselines or space or higher frequencies. We can also look at things like the asymmetry of the ring. That's the ellipticity on the right. And Avery Broderick and colleagues have done a lot of work in understanding how to map these measurements, the ring width and diameter and ellipticity, to properties of the black hole, like spin. So this is just an example of how we're trying to formalize the requirements and understand exactly what's needed. Now, another thing that we heard about was from Priya, and she was telling us about just how important it would be if the ngEHT could actually access a new population of black holes, instead of just looking at 2 targets, if we could see maybe 10 new ones. Is this possible, right? The nightmare is that it's not, and we're just stuck with 2, and it's like heliophysics. We just have special targets we can study. But the other option is maybe it's like LIGO, who took decades to make their first discovery, with many people doubting that they ever would, and then all of a sudden it's an explosion of new events because they have a volumetric scaling. So what will it be for the ngEHT? Well, we think to make a measurement of the black hole mass, it's enough to get the diameter of the emission when you're in the optically thin regime. And an example of this is if you go back to the early EHT papers in 2008 and 2011, these are papers where they were able to measure the ring diameter to comparable accuracy as what we reported in the EHT. If you're confident in making that association, we would have been able to read a black hole mass off those measurements. Now we can also potentially get indirect measurements of the black hole spin through the resolved polarization structure. On the left and the bottom there, you can see just 2 example images of a non-spinning and a rapidly spinning black hole where the pitch angle of the polarization changes between them. Now this is not like the diameter of the shadow. You can't just read it directly off it. It's something you would have to calibrate using theoretical simulations and calibrate using our better measurements of M87. But it's a pathway to be able to get an indirect measurement of spin if we can characterize the polarization structure. So what we did then is we did a study led by Dom Pesci about how many black holes would be observable if you have a particular angular diameter threshold and a particular flux density threshold. So each contour there is telling you if your instrument meets these requirements, how many sources are you sensitive to. You can see that M87 lies just outside the n=1 contour, and Sag-A-Star is of course something that we're lucky to have. Okay, so what we do is we take, again, we generate synthetic data. We generate a little model, it's got polarization, and then we make synthetic ngEHT observations applying all of these different thresholds and trying to be as faithful to real observations as possible. And then we see, with those observations, could we measure the ring diameter and could we measure the polarization structure? So here's an example. All these X's on the bottom, these crosses, are where we don't make a successful measurement. You can see the UV coverage on the bottom. We lose almost all the measurements because they fall below threshold. We cannot make measurements of sources that are that faint with the ngEHT. On the left, here's a source where actually we would have quite a few detections. This is at 10 millijanskys, lots of detections, but it's too small for us to be able to infer the source properties successfully. The filled blue circles are ones where the ngEHT would be able to measure the size of the source, but not its polarized structure. So in that case, we would get a weak estimate of the mass, but no estimate on the spin. The filled green circles are ones where we are able to get the size and also the polarization structure. So you get the mass and the indirect estimate of spin. And the ones that are the rings here are the ones where we actually have enough information that we can discriminate between being a ring or just being a blob on the sky. So that would be the set of gold standard measurements where we say the ngEHT is seeing a population of rings. We're measuring masses from them, and that's our gold standard for black hole mass calibration that Priya was talking about. And if you look at this, you know, there is the possibility of measuring the masses of 50 to 100 supermassive black holes, the spins of 10 to 20, and having this gold standard set of something like 10. So again, this doesn't guarantee that it's possible, but if this had failed, it would really put this goal in jeopardy. So we're moving towards understanding what's needed and really trying to convince ourselves of what's possible. This is the kind of thing that really needs a lot more focused study and is something that I hope others here will engage in. So I just want to advertise again, we have this special issue in Galaxies. This is a chance for us to continue building the science case. It has many layers. There are high-level summaries that have to be substantiated by detailed studies on increasingly microscopic elements of it. So I really encourage everyone to submit. It's refereed and indexed, and it's completely free. So any type of contribution is welcome, and don't hesitate to reach out if you have any questions. And we've included time in all the breakout sessions so that you can discuss white papers, ones that are in progress or ones you want to start with your colleagues here. So to summarize, the EHT images are just our first glimpse of space-time near a black hole, and we know that there's a wealth of new physics to explore. We've had this really exciting community-driven pathway to define the ngEHT science priorities, and I think we've made a huge amount of progress. And I think that this week will be a chance to really close out some of the major issues and be able to lay a roadmap for the future. So thanks all for joining here, and happy to answer questions.
Let's thank Michael. All right, so a wonderful and exciting set of science to do. Inspiring. Do we have a few questions in the audience? Right there, Peter.
Hi, Michael. Is it ever worthwhile to have a mini array of the small dishes, like 3 10-meter dishes in close proximity, or is that never economically or in terms of the added benefit to the array worthwhile?
Yeah, so in EHT, we're really excited about short baselines as a way of tightening up calibration. For a long time, we thought that it might make sense to say partner small dishes at all the ngEHT locations. I think the current thinking is that that's actually not the efficient distribution of sites. You actually get almost all of the information through closure quantities as the array grows. But this is an example where we've done the array exercises. We know where we can put these on the Earth, and we know how to model the weather. Now we have the science goals, and we know some simulations where we can really say what an array is capable of. And I think we need to merge those and understand maybe there are particular goals that would really benefit from a high sensitivity triangle where you need little else. So lots of work to do there, but yeah, we're just getting started. Yeah.
Is that a response to Priya? Is that a response to this line of questioning, or okay?
And can we do anything with CubeSats?
Can we use CubeSats?
Yeah.
That's a pretty interesting question. We have moved away from, initially when we thought about space, we thought about low Earth orbiters. They trace out UV coverage very fast. There's a lot of appealing aspects of that. I think our current thinking is that ground arrays are probably the better use of resources. It's these dishes, to get them large enough to make a detection, they have to be pretty big and pretty bulky, because the surface accuracy requirements of 230 are so stringent. I think if we were doing a 3 millimeter array, CubeSats might be a pretty interesting possibility. So I suspect they're in the future, but probably not in the cards for ngEHT.
All right, thank you for your patience.
Yeah, thanks for the great talk. It was very exciting to see all of this possible science that can be done. Could you just comment on the photon ring? How well can you use it to test the curve metric? And is the photon ring one of the main things that you want to measure to test the curve metric, or are there other things that are even more important, like the variability or something?
Yeah, so absolutely. The photon ring it's a wonderful feature because Once you know all the direct emission, all the fuzzy stuff, all you need to specify is the black hole space-time, and you get the rest of the photon rings for free. There's a self-similar structure. And the black hole is simple. It's described by just 2 parameters. So detecting the photon ring is absolutely a major science driver, and then measuring it and using that to infer properties of the black hole and test properties of space-time, I would say is probably our cleanest approach to getting traction on that question, our least model-dependent approach. So Avery has done a lot of work trying to join those 2 measurements, the direct emission and the photon ring, and be able to say how accurately can we make measurements to the black hole. I think this is really underexplored, to understand how can we test the Kerr metric with this, what types of measurements are the most important? Is it diameter? Is it asymmetry? Is it width? This is something that's really, there's a lot of active exploration, and I know it's a big part of the fundamental physics science case. So they have a breakout room tomorrow, and I really encourage anyone who's interested in the science to attend that.
All right, let's thank Michael again. And anchoring this relay of introductions to the ngEHT, we have Janice Houston, who's systems engineer with the ngEHT project. Who's going to tell us about operations concepts.
So hello, I'm Janice Houston. And earlier this morning, we heard Sarah Markov in her talk talking about some of the challenges that the ngEHT was going to face during the operations. And I'm here to address some of those. All right. But that was a wonderful introduction, Sarah, and thank you for leading into this talk. I'll have to point here. Okay, there we go. As you heard Shep mention earlier, he has a vision. The ngEHT has a vision of what they want this array to be capable of in order to extend the EHT observation. And there's 4 basic components. One, of course, is the addition of 10 new VLB sites. That itself is going to be a very interesting challenge to actually implement. We're going to extend the observations with the increased baselines and UV coverage, which you heard both Shep and Michael talk about. Some of the things that they didn't quite hit on is that one of the major goals is to include 60 days of observation for this community to get beyond the 2-week EHT campaign. And additionally, we want to have different operational modes. You heard the question earlier, was there going to be an ability to have a target of opportunity? And the answer is yes, that is a requirement that has to be implemented. And the way that we're going to achieve this is not to have 60 days of continuous observation, but to have multiple windows throughout the year that will allow like periodic measurements. For example, take an observation every 3 days that would allow this community to make an M87 movie, for example. So how do you take that vision and how do you implement it into a thing? I would like to ask this community here, how many people have actually made an observatory? All right, so we got 4 people who have 4 or 5, 10 people who have made an observatory from the ground up. And the way that you achieve this is by taking that vision and making a set of requirements. And tomorrow, my colleague Aaron Oppenheimer will talk more about how that goes. But you will see that we do have high-level requirements that correspond to the operational modes. And the goal is to increase the number of days, to be nimble, and to have the ability to do co-observing campaigns, warning about multi-wavelength measurements. Earlier, there was a question about proposals, and that is a top-level requirement for this project. Other top-level requirements include being able to perform VLBI measurements, and, for example, shorter time to science. All of this becomes implemented via the operations concept. And I just want to say that right now, the operations concept is in, so shall we say, its baseline state. And you will see as we march through the program and the project, it will evolve, and it will evolve with the input from this community. So how are we going to operate? This is a really big question. I've had a lot of really interesting discussions with Remo, and I appreciate all of his input and his insight. But the array will have its own array operations manager. We'll have two major operational modes, which will be VLBI and non-VLBI. We would obviously want to be able to be compatible with the ngEHT observations, and that is a requirement for us. And then a major requirement for us is to have this ability to monitor the array remotely. And this is partially to keep long-term costs down for the array. So for the operational modes, there's really 4 modes that we're considering at this point in time. If you have additional feedback, I'd like to hear it. But the modes are a single track, which would be 1 observation per night, then a multiple track over multiple days. The periodic mode, which is an observation that has a cadence once every 3 days, once a month. We've heard some discussions earlier about people wanting to have observations in a multi-year time frame, and that would be feasible. And then the target of opportunity, driven by the need from the astronomical observatory community to observe something real time. And our requirement is to be able to respond to that request within 1 day. So that's sort of like the vision and the goal, which translates to level 1 requirements. But how are we going to actually demonstrate that? How are we going to demonstrate that this is feasible relatively quickly before a large investment happens in the project? Well, we're going to do that with the LMT and OVRO upgrades. Remo talked about that a little bit earlier in this presentation, but there is now currently a team effort with people from SAO, Caltech, Berkeley, and UMass Amherst that are currently working together and are planning how to conduct the LMT OVRO demonstration. And that is going to include an upgraded receiver, and you'll hear Gopal talk a little bit about that more on Friday. A new upgraded digital backends, which my colleague Rajni is also going to talk about on Friday. And we're going to show and demonstrate that this can work within the next 2 years. And this is going to involve a handoff. Gopal is going to have to go to LMT, uninstall the LoRa receiver that's currently at the telescope, ship it to OVRO, we'll install that equipment there, and that will effectively make OVRO an EHT telescope. And then we'll take the new receiver, the dual band receiver that Gopal is building at UMass, install it at LMT, and then we will distribute and install the 2 digital backends that Raji is making at each site. And that will be basically the instrument for those 2 telescopes. Then we're going to conduct a fringe test at 230 gigahertz. And we're going to only do the 1 frequency because of some other limitations at OVRO. But our goal is to have this all accomplished, the hardware developed, tested in the lab, sent to these 2 telescope sites, in order to be prepared for the 2024 EHT campaign. It's an ambitious goal, but I think it is achievable. But we may have some unique challenges with the supply chain. So just stay tuned with that. But this is a great opportunity for this community. I think it's a great opportunity for the early career scientists if they would like to participate in this fringe test. And if you do, please contact me because I am open and receptive to adding team members. Regarding the timeline, I asked that question earlier, who has built an observatory? Well, how this is done is through sort of a systems engineering process. This process is sort of tried and true. But we've had our systems requirements review. We just successfully completed that a couple of weeks ago. we're marching to a conceptual design review in the fall timeframe. And in between those two events, we're going to have what we're calling an engineering busy week. It's either going to be the week of July 15th or July 23rd. And again, this is another opportunity for the community to participate. We're going to be talking about what we really want the array design to be. And maybe you might have some unique requirements or some unique desires that you would like us to hear about. And this is the time. This is the time because after we come up with a concept design to get somewhat fixed, because we're going to be building to that thing. And part of the operations concept is to take that thing that we're going to build and figure out how to operate it early. And like I said, we're going to do some demonstration of that at OVRO. And then we will march to a PDR next summer, which will be the preliminary design review. And then we'll go work towards the CDR. But this here is a very busy year. So by next summer, we should be in the PDR timeframe. And what's really interesting is before we get to the PDR, is we have really basically committed to the receiver and the digital backend design. And that is why the OVRO test is so critical. Because if we need to make any changes, we can do it before the 2024 time period. And we have test objectives, defined test objectives that the team has already put together. But basically, we want to bring OVRO online as an ngEHT telescope. And we need to demonstrate the interoperability of the equipment because we will, the ultimate goal is to work with the ngEHT. And that already has equipment that they've used successfully. And we need to be able to communicate with that equipment as it is. We are going to demonstrate cloud correlation. This will be a new data processing technique, shall we say, to help us achieve that goal of faster time for science. And we're going to exercise our monitor and control system. And for me, very critically, we're going to operate as I would like to as part of the operations plan. The operations plan comes after this operations concept. For the near-term work to close out this activity, there's a lot of steps. And one of the things we're going to do is we're going to have an interface control workshop in the August timeframe. Make sure we have all the interfaces defined. And this is very critical because having the interfaces defined between the receiver, the digital backend, and the LNT telescope and OVRO telescope will inform the design and the interfaces for the brand new ngEHT telescopes and help define the interfaces to the BEMA telescope. There is a trade study. The logical question is, if you have a dual band receiver, you're only going to test out one frequency, why aren't you going to test out the other frequency, the 345 gigahertz? And we have a trade study underway to determine if we want to add a third station, such as JCMT, to this fringe test. Okay, so that's sort of early operations. That's an early technological effort. But then what is the vision for actually operating the array when it's developed? It's a little bit of a challenge, right? When you look at the next decade, we are going to concurrently build, design, and implement over multiple years because we're going to build 10 new stations. And so we can see here in the schedule, we're going to have 5 sites per phase. So the first phase, as Shep and Michael both mentioned, is 5 sites. And the effort and the goal is to have that work completed by 2028, come up with 5 additional sites, and complete that work by 2030 and be online as a 10-station array in the next decade. That requires building out the sites and upgrading also the ngEHT sites. And we heard this wonderful plan from Remo to begin that work now. But then I think the critical and key thing is from the very first ngEHT site, which will be OVRO in 2024, we will be able to participate in the ngEHT campaigns. And every time we have a station come online, we will be adding another baseline and we will be adding more information to the UV point. So phase 1, you've heard both Shep and Michael talk about what this looks like. I'm a really big fan of phase 1. I actually really like these sites. And as Michael said, these are sites that are under some study. You'll hear my colleague, Daniel, talk more about the site selection process on Friday. But what I like about these sites from an engineering perspective versus the scientific perspective is I think this is achievable and implementable in the time frame that we have laid out. Namely because OVRO and KSTAT already exist. OVRO, the team has a lot of history with, and KSTAT is just right down the road from Cambridge. And I think what I like about Canary Islands, Baja, and Los Campañas is it allows us to demonstrate the capability with the BEMA 6-meter dishes. Okay, it allows us to figure out all the things that we need to do, which are just engineering challenges, the logistics of shipping a telescope from one place to another, installing it on site. And I think it's implementable because I think it's well defined, and because Canary Islands and Baja are already standalone telescope facilities that already have a lot of base infrastructure in place. The other thing I like about the phase 1 is it allows us to work out any potential engineering issues that we can have with software or other unexpected issues. So it's a great way to extend the existing HT array and yet have a test bed for the phase 2 stations. In phase 2, it's under consideration right now about what these sites are. And as Michael says, they're not set, but being consistent with the array that the scientists are using for the simulation, all the sites have been identified. And there's also an effort underway to consider if we should include 86 gigahertz. And Sarah will be talking about this on Friday. I would expect as the site selection continues, as we learn from our phase 1 implementation, you could see some changes to these locations. I'm going to thank Jeff Bauer and Remo for helping me with this chart. But Jeff had shown earlier on Sunday the history of the EHT campaigns and the wonderful work that the HTC has performed over the last half decade. And what I've done is extended that to show you what we can look like in this decade as we extend. And you can see here in this plot, these are the baselines of the EHT. And by adding the stations for the ngEHT as they've been identified here, you can see that we can get almost up to 200 baselines, additional baselines by the end of the decade. The things to note as we go through the calendar year, these include the upgrades for the receiver, the digital backend, the addition of the BEMA dishes, and then as you go into the phase 2, you can see the nomenclature for the addition of the new dishes. But there's a great deal of upgrading that occurs during this life cycle period. And as like Remo said earlier, this is a dynamic implementation plan. We are not just taking one Lego piece and multiplying it 10 times. There's a great deal of evolution that happens in this implementation. There's been a lot of questions I received offline about what are the station operations going to look like. And this is a key component to the ngEHT program with the vision that each partner institute will maintain and operate each station locally. And I think this is important from a buy-in perspective. It's also important from an engineering perspective, because that means that the station partner is responsible for the operation, the maintenance, and logistics. And there's a lot of coordination with the ngEHT operations manager. The other idea that we want to implement is that the station provides the locally trained personnel, and we provide the VLBI support remotely. And I think we've observed some of that during the EHT campaigns already. Just to sort of wrap this up, in 2030, at the end of this decade, the ngEHT array will be completed. I think that is feasible. It's going to be managed by our operations manager. And for the observations, when we initiate, a large part of the observational campaign is going to be concurrent with the HT observations, which occurs in the normally time frame that we already experienced, which is 2 weeks in March and April. And that anchor station is typically ALMA. But like Michael said, the rest of the time, for the other 40-ish days, we will observe as an array with a large anchor station such as LMT for the other 45 days of the year or so. I just want to leave one thought before I conclude my talk, that with this vision, by implementing this vision, this provides this community a very unique opportunity to be on the groundbreaking floor of a huge telescope development effort that will lead to the ability for these young career scientists to maybe be here in the mid-2030s with your grad students and your postdocs talking about the discoveries you made with this system. Thank you.
Thank you, Janice. So can I use my prerogative and raise the question that Svetlana asked before about, you mentioned target of opportunity modes, but I think 1 day was the time scale. What's the shortest that you could possibly envision that shrinking to?
So the first time I wrote the target of opportunity requirement, I asked for a 10-minute response time. And Vikram Ravi from Caltech, who is our point of contact at OVRO, initially looked at that and said that may not be feasible. And so we are going to talk about a stretch goal within the requirement. And I would like to get it down to the hour time frame, but we will need to simulate and demonstrate that during the OVRO fringe test to really see what is achievable. And obviously it could be for some other telescope sites that are not within the ngEHT operations manager prerogative, but that is not feasible. So the requirement would only be levied on the ngEHT telescopes.
Thank you. David, you have a question.
Yeah, thank you for that talk. Forgive me if I misrepresented your basic requirements, but it sounded like the expectation is that you have 60 nights a year, open access to open time proposals, and also, again, talking about this opportunity for targets of opportunity. So how strict are those requirements? For example, in the case of the LMT, we have new instruments that are coming that will have a huge demand for the 1 millimeter time over the next 10 years. The 1 millimeter time is limited. We have a community that has a broad scientific interests using other instruments. We don't have open time proposals. And we will also have our own targets of opportunity. So how critical is it that all of the facilities fulfill, those basic requirements of the ngEHT?
So if I can just walk that back to not be specific to the LMT, but to be generic, because I think this is a question that applies to all the future stations, shall we say? And I think the reality is that as we go through this development process, the ngEHT program manager is going to have a unique and challenging job, as that person has to formulate the specific agreements with each station. Okay, and the initial request to fulfill the requirement would have to be 60 days. And then as the negotiation would continue, there would be discussions about each availability for each site. But then let's narrow this question down to a little bit for LMT. So hypothetically, for that type of station, I think it's a realistic expectation to have talks and negotiations about, is it possible to buy a share? Because there could be, depending upon the partnership arrangement of each telescope site, which we all know is unique and individual, those are the type of opportunities that would have to be discussed.
But just to give some context, you're talking 30% of the available telescope time at 1 millimeter for multiple years. So
Yes.
that's your expectation.
I think that's the goal, and the requirement is now, and as we go through the project, we'll have to see if that is achievable. And I think we have to remember that this is a very dynamic situation. Like you said, you may be booked out for 10 years now, but what does that mean for 2035? Is that really booked out now? And I think that's really when you think about the full ngEHT array, about where the negotiations are going to come in. Because we are going to be developing through this decade. So I think this decade's performance will be different, what we'll be able to do in the 2030s. And I think as the astronomy community sees what we can achieve during this time frame, and then as the participation grows and the science needs are solidified and expanded, so I expect it to expand as people see the capability of the array, I think that will influence the discussions and the arrangements in the 2030s.
All right, last question. Jeff.
So as a scientist, I'm excited by the possibility of a steady cadence of observations to movies. However, on the operational side, we're trying to do, I wouldn't say cadence, but just, hey, try to observe M87 on 3 nights and not back to back. And the operational challenges to doing that are not really the hardware, although there are problems with that, but the weather. Even at a fine site like Alma, it's really not realistic to expect to get, a usable night every 3rd night for 2 months. That just is not going to happen. And if you drop a frame or here or there at a particular site, maybe that's what you're planning to do. But I also think you add it all together across all the sites, and it begins to be far less than what you plan to do. And I was wondering if you've been having discussions about just how to cope with the reality that you're almost certainly going to have.
So I think there's 2 answers to that. I think within the extended EHT array, with the telescopes that exist now, like you mentioned, like ALMA, I think that'll be a challenge, as you mentioned. But I think the operations with the ngEHT array will be more within the domain of the ngEHT operations manager. So there will be, at that point in time, then weather limitations, and that's when we'll rely on the science team with their simulations to discuss, does it have to be every 3 nights? Can it be 2 nights and then 4 nights? And then I think from a reality standpoint, is the scientific team is going to have to look at the data as we go through, especially as we test out some of these situations and these operational modes to see what works and doesn't work, and then adjust accordingly.
All right, so let's thank Janice again and all the speakers in the session. And don't run away just yet. I think Angela is going to give us an announcement.